Hey everyone. So welcome to this next lecture in the Deep Learning from Scratch series. And in this lecture, we're now going to build our first multi-layer neural network, right? We're going to go through a little theory first, and then we are going to implement this in Python, right? And so we've previously seen how a single neuron model works. We've implemented a model for regression. We've done logistic regression, and we've trained one neuron for a regression problem for price prediction, right? And so this is important because now we're going to build on this, but now see how we can take those neurons and connect it into a network. And we're going to focus here on a feed-forward neural network, which means the data comes in and then computation happens. So the first layer is there is the inputs. So it's the input layer. Then and the data just keeps moving forward, right? In the forward pass, it's kept the data, the values are computed here. The outputs are fed forward to the next layer, and so till you get the prediction from the net. Um, and each neuron here is effectively a neuron like we saw in the single neuron model, right? Only it would have a different activation function, right? And in this case, we're using a tanh activation. So how would you assemble neurons, right? The answer is simple. The way it's done for neural networks is neurons are assembled into layers. So you have the two inputs. You've kept them outside. Assume this is the first layer in that net, right? And so you have three neurons. I'm calling them N1, N2, and N3. Now, the neurons in a layer do not interact with each other. They are independent of each other. They have their own sets of weights and biases. So this will have its own set of weights, this will have its own set of weights, and this will have its own set of weights. It will also have its own bias. And then what will happen is the inputs, right, from the previous layer, or in this case, it's the first layer, let's say. So the inputs, what we saw in a single node model, the inputs are passed into that neuron. What will happen is the inputs are actually passed into every single neuron separately. So this is neuron one, right? Now we're using some basic nomenclature here. We're going to say that the weights and the bias in this calculation, it's a bit obscured, but the weights and the bias, you'll see that for each value, it's going to be written this way, where the superscript here is the layer that the neuron belongs to, and then the J and the I indicate which input it's coming from and which neuron it's coming to in that layer. So in this case, there's just one layer, but then you have, in this case, the weight associated with this particular input will be W1, layer 1, J, so input 1, and it will be the corresponding first neuron. So it will be N1. This will be W1, J will be 2 because it's the second input of that layer, and I, this is the first neuron. If you look at the second neuron and the inputs come to this neuron, then what will happen? You will have W1 because it's still layer 1. But then you will have J, this is 1, first input, to I is 2, I is the second neuron, and so on. So we'll see this in examples. So I figured I'd put it right there. So for the first neuron, you have an activation function. You have the standard sum of the weights, the product of the weights with the inputs plus the bias. So W1, because it's layer 1, and then it's just WIXI, input 1 times the weight associated with that, input 2 times the weight associated with that for neuron 1. For neuron 2, it's the same. And the output is going to be A, layer 1, neuron 1, right? So this is now neuron 2. The same two inputs are going into that. So the inputs, and so this is called a fully connected network that we're going to be looking at. And so every input in the previous layer is passed to every neuron in the next layer. In this case, it's the first layer. So what you have are the inputs to the network, and the inputs, every input is passed in to every neuron, right? Or rather, every dimension of the input is passed to the neuron. So for A2, it's the sum of, again, the W of layer 1, and this is neuron 2, product of the weights associated with these inputs. And they're separate to the weights in the first neuron. They're their own set of weights, right? And the corresponding bias. And then you have the third, and it's associated weights with that and the bias with that. And the same two inputs are passed to that neuron. So you see how a layer works, right? Inputs from the previous layer, the outputs of the previous layer are passed to every single neuron. The neurons are independent of each other. They take those inputs, run the standard neuron operator. So you can think of each neuron here as that single neuron. Only now they're computing for each of these inputs, it's computing its output. And this now, so in this case, this layer now is three neurons. It's gone from two inputs to three outputs. And these outputs are passed to the next layer. And so you can think of this layer now, when you think of it as a layer level, as having two inputs in this particular case, and it's got three outputs, right? Because each neuron is giving you one output. Next question, how many parameters? So in the single node model we saw, you just had one neuron, so the parameters were its weight and its bias. In this case, this layer itself now has three neurons. Each neuron in this particular case has two weights and a bias because it's got two inputs coming into it. So you've got 3 times 2 plus 1, which is 3 times 3, which is 9 parameters in this one layer. And of course, you'd have many more layers in a neural network. And if you look at more, large complex models like say, Chat GPT or GPT and so on, they'd have millions, billions, and now you have trillions of parameters, right? So you can imagine what the layers are. They're of course more complex layers, right? They're not these simple Tanh layers. And so now that we've seen, you have one layer. Now in a network, you'd have multiple layers, right? And so the first layer in a neural network is basically the input layer, and it does nothing. It just takes the inputs and passes it on to the next layer. And so the first layer is called the input layer. The next set of layers are called the hidden layers, right? And then what you have last is the output layer. This is the output that returns the prediction. So the output and the input makes sense. Why are these called hidden layers? The answer is the inputs coming into the network and you see the output. You actually don't see the values in the hidden layer, or you don't see what the hidden layer is really doing. Although there's a lot of work going on now to try and visualize or understand what's happening inside a network. But the way networks are set up, you don't actually see what's happening internally. You just see, the input and the output. And so these are called hidden layers. And so now you've probably heard the term shallow networks and deep networks, right? So what's the difference? So if you have a simple network like this, where you have an input layer and you have an output layer, now in the single neuron model, you just had the input layer and the neuron, which was the output layer, right? You could have one hidden layer. And so that would be called a shallow network. On the other hand, if you have quite a few hidden layers, it becomes a deep network. And there's no exact number of the number of hidden layers, but if it's one or even two hidden layers, it's typically called a shallow network. In a lot of places, people say 3 plus hidden layers is a deep learning model or a deep neural network. And so if you're kind of running a complex convolutional net to handle images or a transformer model, you will have many more layers. And so those are really good examples of deep learning models. And the reason the number of layers matters is at the end of the day, even if it's the same number of neurons, it's been found that by adding layers rather than increasing the number of neurons in a layer, adding layers or adding depth improves the quality of predictions. Right? Okay. And so let's look at a couple of examples of a deep learning models. We'll just work quickly through the forward and backward pass, and then we can go and implement it. Now, in this lecture, we're going to be using the Tanh neuron, right? And so just a quick review. We've seen this in the lecture on backpropagation, where we kind of did a forward and a backward pass through an expression, which turned out to be the Tanh expression, right? Or the Tanh neuron. Basically, we've got the linear part, which takes the sum of the inputs, product of the inputs with the weights, and then adds the bias. You get Z, which is the intermediate variable, and then the activation function is the Tanh function. And the Tanh function, as we've seen, takes an input, in this case Z, and squishes it to be between -1 and 1. So very negative values kind of get set to -1. Then in this range, so you see somewhere between -3 and say 3, it's kind of active, going from -1 to 1. And then when it starts hitting large positive numbers, even around 5 and so on, the value now is kind of set to 1. This is kind of what a Tanh function looks like. And so what you'd see is this, which we've already seen here. What we're also going to do is, we've already seen in the backpropagation lecture, and I'll add a link to that. We've seen in detail, so do go check that out if if you haven't seen it or you want to refresh how the backward pass works for this neuron, right? And when we code it up, we'll code it up step by step. But Basically, we see that the derivative of the output with respect to the inputs is basically the weight, corresponding weight times 1 minus a square, which is the derivative of the tanh function, rather of the output with respect to z, right? So it's the backprop through the tanh function. The derivative of the output of the neuron with respect to the weight is again 1 minus a square times the corresponding x or input. And the derivative of the output with respect to the bias is just 1 minus a square because the local derivative here is 1. So just a refresher of this, because when we go through the theory now, I'm going to work through this. I'm not going to show you every step. I'm going to assume you kind of remember this and you can work it out, right? So let's take this simple kind of two-layer neural network where each layer now has two neurons, right? Has one neuron, right? So layer one has one neuron, layer two is one neuron. Giving you the weights for each of these. Now, layer one has two inputs coming in 0.2 and 0.1, which means it has two weights and a bias. Layer two just takes this output of layer one, which has only got one neuron. So this neuron now, neuron two, has just one weight and a bias. And the input now, if you write it as a layer, we're writing this as a column vector, is 0.2 and 0.1. So let's take the forward pass now. Take this first neuron, first layer, it's got one neuron. We're running this as a scalar network. So what we're going to assume is the neurons don't interact with each other in that layer, but there's only one neuron, right? So you take neuron one, got the values, you pass in 0.2 and 0.1. So you do the weighted average of that, you get the Z. And then what you do is do the tanh of that. And so what this neuron gives you is 0.1488, right? And it's a 2x1 layer because it's taking two inputs, but now giving you one out. So we've forward passed through that to get 0.1488. That now gets passed to the next layer. The next layer has only one neuron, so it gets passed to that neuron. And so neuron 2 now, we've got the parameters, takes this input in, multiplies the corresponding weight, adds the bias, passes it through the tanh, and you get the output of the second neuron, which is also the only output of the second layer, and that is your prediction of your neural net. So we've done the forward pass. We've now got two layers, each layer with one neuron, and we've got the forward pass. Now we want to do the backward. We're not showing you the loss function. We're just saying that there is a loss function which gives you a loss, because to do the backward pass, you need the derivative of the loss function with respect to the output of the network. In this case, it's with respect to A12 or A21, layer 2, neuron 1. And we're saying that, right, the derivative is 1. The value we've got, the derivative is 1. We've already seen how to backward pass through this neuron, right? As we've said, we've just shown you the values. So the derivative with respect to the weight of this neuron, there's only one weight, is you're chaining what's this, which is the derivative of the output of the loss with respect to the output. You're chaining that with the local derivative, right? Which we've just seen in the review, right? Of the tanh function. We know what the derivative of the output, the derivative of the output of layer 2, neuron 1, which is this, with respect to its weight is. So you're chaining this derivative that you've got from the loss with the local derivative to get the derivative of the weight. You're doing the same for the bias. So this is what you get from the loss function. And this is the local derivative of the output of that neuron with respect to its bias, and you get the value. And the sensitivities that are passed back, right? So with respect to the input to this neuron, which is also the output of the previous neuron, right? Of the previous layer, right? So what you do there, again, you take this, you chain it with the derivative of the output of this with respect to the input, which we know again, and you get the answer to that, right? So this is again chain of this times the tanh times the corresponding weight, which in this case is 0.2, and you get the output. So what happens at this layer? You get the sensitivity with this with respect to the of the loss with respect to the parameters by just taking the value from the loss function, the derivative from the loss function, and just propagating it back. What you also get is the derivative, or rather chain ruling it. What you get here now is the derivative of the loss with respect to the input to this neuron. And the input to this neuron, which is the only neuron in that layer, is the output of this neuron in the previous layer, right? So what do? We pass it back to this neuron. And now what we can do is take this neuron and run the backward pass through that. So now we've got this derivative of the loss with respect to this output. We know the output of the neuron from the forward pass. We apply the same formula, right? Only now we're using this value. So do L do A11 is this value. We already know the formula for the sensitivity of the um, weight of that neuron with respect to its output. We have two weights, so we do that for both the weights. We do the same thing for the bias. I've put these values here because what I'd suggest is you take a piece of paper and just work these out, right? You know the formula, so it's just substitute. But it's a good test to understand how this works. So you've got that, and we don't need the derivative with respect to the sensitivity with respect to the inputs, right? We only need it with respect to the parameters. So we've done the forward pass through both these layers, and then we've taken the loss and propagated it back to these two layers. The only advantage we had here was each layer had only one neuron. So it's very similar to what we did with the single node model. But you see how it works. And I haven't worked through each of these numbers because we've seen a little bit of this in the back propagation and in the single neuron. So you know how the calculation works. The interesting part is how you chain the values from one layer and pass it back to the previous layer. So for this layer, one neuron, you've got the sensitivity with respect to the parameters. Sensitivity with respect to the inputs doesn't matter because it's the first layer in the network, or rather the first hidden layer. What is before is the input layer. And so this is a summary of this network where we've done one forward pass and one backward pass. And with the backward pass, for this set of inputs and for a given loss value, we've got the sensitivity of the parameters of the loss with respect to the parameters of neuron 1 and neuron 2. So this kind of seems quite familiar, right? Okay. So now what we're going to do is do something more interesting. We're going to take a more complicated network. This network now has the input layer. It's got two hidden layers, L1 and L2. Each layer has two neurons, right? And then you have the output layer, L3. And so you will see a slightly more interesting set of dynamics. So let's start with the forward pass. The forward pass is fairly straightforward, right? You have neuron 1 and neuron 2. Each neuron takes both the inputs from the previous layer, right? It's a fully connected feed-forward network. Fully connected means the input X1 goes to both neurons, the input X2 goes to both. And actually, it's passed as X1, X2. This neuron has two weights and a bias because it's got two inputs. This neuron has also got two weights and a bias. Now, how is this executed? Because in the previous example, you had one layer and you had one neuron. So you executed that, then you moved it to the next layer and you executed that neuron, right? Well, the neurons are independent. So actually, it doesn't matter which order you executed it. You take neuron 1, we're going to take neuron 1. We're going to execute neuron 1, the forward pass through it, and we are going to get, so it's going to take the inputs, run the forward pass, get the output, and that output now needs to go to the next layer. We aren't passing it there yet. What we'll do is take these inputs, pass it to neuron 2. And neuron 2 runs the same set of operations with its set of weights and bias and gets another output. And then what we do is we take those outputs and we pass it to the next layer. And so how that is done is the output for that layer is the output of neuron 1 and the output of neuron 2. And that now is passed to the next layer. And so I'm showing you here that this output is coming here and here, and this output is coming here and here. But actually now we've agglomerated or collected the outputs for that layer. We're passing the outputs now to the next layer. So what does the next layer do? The next layer takes this, which was the output of the first hidden layer. This layer, layer 2, takes that as its input, right? If you look previously, here the inputs were X1 and X2. Now the inputs have become A11, output of layer 1, neuron 1, and output of layer 1, neuron 2, which is now A1, which is the output of layer 1 as its input. It's got two neurons, so they've got N3 and N4. Two neurons, each neuron has two inputs, right? Both the inputs are passed to each neuron. So it's got two weights and a bias. It's got two weights and a bias. You run it exactly like you did N1 and N2. They're independent of each other. So you run N3. You take these inputs. So now it's the weight times A11 and next weight times A12 plus the bias, you get the output of that neuron. Similarly, for N4, you have its weights and bias. You kind of use the input A11 and A12, run it through that neuron, and you get the output of that neuron. And so now that layer now gives you the output of layer 2 is A21 and A22, which we've just computed. That is now passed to the next layer. And so now N5, and this is the last layer or the output layer of the network. What does it take in? It takes in A2, which was the output of layer 2. It takes in A21 and A22. It's got its weight and bias. So third layer, first neuron, third layer, weight connecting the first neuron of the previous layer to this neuron. Third layer, weight connecting the output of the second neuron in the previous layer to this, and the bias. You'd run the standard Tanh forward pass. You get the output of this layer. It's only got one neuron, so the output of that layer is basically this, which is your prediction for the neural network because it's the output of the neural network. So we've done a forward pass now through a network with two hidden layers and the output layer, right? So it's technically 4 layers, right? I said 3 because I'm not counting the input. So without the input, it's 3 layers. If you count the input, it's a 4-layer net. We've done the forward pass. What are we left with? The backward pass, right? So first thing we need, assume a loss function. And for now, we're assuming the loss function is returning a sensitivity of the loss with respect to this output. So DL, the A3, 1, which is neuron 5, the output of that is 1. The derivative of the loss with respect to that is 1. So what do? We backpropagate through this neuron. We know how to backpropagate through a neuron, right? We've done it quite a few times now. What does this neuron have? Its inputs, which is A2, its output, which we've got from the forward pass, and its parameters. How do we backpropagate? Exactly like you do through any other neuron. You take you want the derivative of the loss with respect to its weight, or with both its weights. You take the derivative that you've got from the previous layer that's been propagated back. So in this case, it's the derivative with respect to its output. And then you take the local derivative, the derivative of the output with respect to its weight, which we know is just what you had, times the derivative through the tanh, times, in this case, it's with the weight. So it's the corresponding input, right? It's this 0.1973. And you get the output. Or rather, you get the derivative. You do the same for the second weight and for the bias. And you've got the derivative of the parameters of that neuron. What you also need, well, there's a layer before this. So you need to propagate this back. So in the previous example, we did that for one neuron. In this case, you're propagating back to 2 neurons. So you've got 2 inputs coming in, which means you have to get the sensitivity of the loss with respect to both of these inputs. So you take dual do A1, 2, right? So it's A21 rather. So it's layer 2, first neuron, which is N3. The derivative of the loss with respect to the output of that is, well, it's exactly the same thing, right? We know the formula for that. It's what the derivative of this output chained with the internal derivative. Do A31 with respect to do A21. You know the formula. It's what was passed in chained with the derivative of the tanh because it's tanh activation with the corresponding weight, right? We've just seen this in the review. You've got the output of that. And you do that for this and for this. So the input coming in from N3 and the input coming in from N4, you get both those sensitivities. And so at the end of this first step of this backward pass, we've gone through just N5. What have we got? We've got the derivative of the parameters of N5, which is this layer. What we've also got is the sensitivities with respect to the inputs to that layer, which is just one neuron. So we've got dual do A21, which has to be passed to N3, and dual do A22, which has to be passed to N4, because that's where the inputs come from. So you just take the backward pass, you take the inputs. If there was just one neuron in the past, you just pass that back to that neuron. You have 2 neurons. You see which input's coming from neuron 3, and you pass the sensitivity with respect to that input back to that neuron, right here. And with respect to neuron 4, same thing. You see the input that's coming in from neuron 4 and pass the corresponding sensitivity back to neuron 4. So we've now done. Now, if you have, what if you had three neurons in this layer? You would have three inputs, which means the do input would have three values. You would have do A, 2, 3 as well, right? Because you would have three neurons. You pass that back to the third neuron. So you can have as many neurons in this layer, and the process is exactly this. So now we're there in that layer. What do we do now? So we are propagating now back to this layer, right? And so to propagate to this layer, well, we've got now the inputs to that layer, which we know from the forward pass. We know the output of that layer from the forward pass. What we also have now that has been back propagated from layer 3, from the neuron N5, is the sensitivity of the loss with respect to the output of N3, which is do L, do A2, 1, layer 2, neuron 1, and do L, A2, 2, which we know, right? We've just got. We also have the parameters. So now, well, you can do either neuron. We'll start with neuron 3. They're independent of each other. So we can pick whichever one we want. I'm going to start with 3. And I'm going to say neuron 3. And you just do the back propagation through that. So you get the loss with respect to the weights, which is just done by chaining what you've passed back from neuron 5, right? And computing the local sensitivity. And you do that, and you get the output of that. You get the derivative with respect to the weight. So when you get to that neuron, once you have the value or the derivative of the output, then that neuron just performs, just think of it as a single neuron, right? And you just, the back propagation just is performed exactly the same way. So you get the derivative with respect to the two weights and the bias of this neuron, right? And then what do we have? We have the sensitivity with respect to the inputs to this neuron, which is what you get from N1 and what you get from N2, right? So it's do L, layer 1, output 1, and do L with respect to layer 2, layer 1, output 2, right? So which are the inputs to this neuron? You get that. So this is exactly what we did in N5. What's interesting though is, and let's do N4, the neuron 4, which is the second neuron in this layer. So the inputs coming in, now you take, and so in the previous one, actually, the input coming into this, from the previous layer, you had do L A21. This is neuron 1, layer 2. So that's what is used. In this one, you have what is used is do L with respect to the output of neuron 2 of layer 2. So this is what is used. So you see in the calculation here, the output of this neuron is used. And so you get the sensitivity of the weights of this neuron and the bias using the standard Tanh formula, right? You've taken what has been passed back, and what you're doing is, so 0.1439 is used here. So you take what has been passed back, and you take the local sensitivity and the sensitivity with respect to Z, right? So this is the Tanh sensitivity, and this is, in this case, the bias, and you get the output, right? Same for the weights. And then you get the sensitivity again with respect to the inputs. So again, you've got the sensitivity with respect to the input coming from N1, which is A11, and coming from N2, which is A12, the output of 1 and 2. So when we've done the backward pass for this layer, it was simple because we got the sensitivity with respect to these two outputs, apart from the sensitivity of the neurons parameters. We passed it back here and we passed it back here. What happens here? The sensitivity of the parameters is straightforward. We have two neurons. So layer 2, weight 1, 1, weight 2, 1, and bias 1. Layer 2, weight 1, 2, 2, 2, and bias 2. That's okay. What about the inputs? Well, actually now, this neuron has what needs to be propagated back to this neuron in the previous layer and this neuron in the previous layer. But this neuron also has inputs coming from both those neurons, right? So it also has something, or rather a sensitivity that needs to be propagated back to neuron 1 and neuron 2. So you have two sets of values, right? Now what you could do is call the backward from this, pass it back to this neuron, and call the backward from this and pass it back. What we are going to do here is, because it's the same layer, we're going to add those two values, which is what happens at the neuron anyway. So we're going to add that, and we get for that layer sensitivity with respect to this input, which is obtained by accumulating the sensitivities from N3 and N4 for this input. And the same thing for this input, for A2, right? A12, we're going to take what you get from N3 and N4, add it up, and then you're going to pass it. And so that's what we've done here. So once that is done, we've propagated that back to N1 and propagated that back to N2. And so now you go to layer N1. And now what you have? You have the inputs to that layer, which is the inputs to the network. You have the output of the neurons. You have output for N1 and N2 for layer 1. And layer 1 now has got the sensitivities of the loss with respect to A11 and A12 passed back from the layer ahead of it. For neuron 1, you take the first part, you take the sensitivity of the output of neuron 1, and you run the standard chain rule backward pass through that neuron, right? You have the value that's been passed back. You compute the local sensitivity with respect to the weights of the output, and you chain it. You do the same for the second weight and the bias. And with the input, you don't care anymore because you're at the first layer of the network, or rather the first hidden layer, and what's before this is the input. For layer N2, you do the same thing, which is this neuron now, neuron N2, which is this neuron in this layer. You run the backward pass through this with this value that's been passed back from the previous layer, right? So you get the sensitivity with respect to its weight, its bias. And again, you don't care about the inputs. But now what you've used to do the chain rule is what's been passed back, which is the dou L, dou A12. So what's been passed back is for this layer, you've taken the second value in, right? And so you've got for the first layer now the sensitivity with respect to the weights and the bias, and you don't need the sensitivity with respect to the inputs because that is now the first hidden layer. What's before it is the input layer. We don't need the sensitivity with respect to the inputs when we do a gradient descent. So by going through the forward and the backward pass for a given set of inputs, we've got the sensitivities of all the parameters of this network. How many parameters are there? First layer, 2 neurons. Each neuron has 2 weights and a bias. The first layer and the second layer have 6 parameters, and the third layer, which is the output layer, has 1 neuron, or rather the fourth layer, if you're counting the input layer, has 1 neuron. So it's got 3. So 6 plus 6 plus 3 is 15 parameters for this neuron. Now you'll also hear the term hyperparameters. Now we'll cover this more when we start getting to training a network. But basically, hyperparameters, for example, for a network like this, are the number of layers, how many neurons are there in each layer, and what are the activation functions used. And then there are more depending on the parameters that are used when you're training. So the gradient descent parameters. So the parameters of the network are the actual weights and the biases for this type of neural network. And for the hyperparameters are, the bigger picture parameters, like how many layers you use and how many neurons you use in the layer. And the number of neurons in the layer determines the number of outputs of that layer, right? If you have 5 neurons, it's 5 outputs, right? So that is a hyperparameter. And what activation function? We've used the Tanh activation function. So that's a hyperparameter. Now, one thing to keep in mind when you start having multiple layers is the number of inputs of the previous layer, the number of outputs from the previous layer is basically the number of inputs coming to this layer. So in this case, it's 3 neurons, but the previous layer has 4 neurons. And so each neuron here now gets 4 inputs. So you need to keep the dimension, right, in your head, right, and make sure dimensional compatibility is correct. We'll go through this a little more in detail when we get to the vectorization part, because there keeping dimensions in mind is very key. So we'll start with this when we do that lecture. But let's for now go and now take this neural network that we've created and go and implement this in Python. So let's get ready, open up the Jupyter notebooks, and let's go. Okay, so let's now get started implementing our neural network. And we're going to start by first putting together a tanh neuron quickly, and then we'll take that and assemble it into layers, and then we'll take those layers and assemble layers into a network, right? So just 2 imports. We're going to import numpy. I'm going to import GraphViz. Now, if you're not familiar with GraphViz, we've used it in the single node module lectures as well. It's basically a really nice tool that helps you visualize graphs, right? So you can go to graphviz.org and you can check it out. And you can install it using Anaconda. We've used that to install or set up everything else. And so it's a simple function called Viz Neurons. I'm not really going to spend a lot of time on this. It's using GraphViz. We've set this up. And what it does is it takes in a layers, which is basically a list of neurons, right? So when we kind of build a network and then pass in the layers, you'll see what this does. But basically, it takes in a list of neurons. And what it does is it loops over the layers and then visualizes the neurons as nodes, right, in the network. And then what it does is creates the edges between those nodes as well. And then it'll populate that with the weights, the sensitivities, so that you can see what's happening. Right? So I'm not really going to spend a lot of time on this. If there's time at the end of the series, I can put a short tutorial on GraphWiz, and you can also see how this works. Right? It's very simple code. You can loop over the layers. And once you loop over the layers IL is basically the list of neurons. And then you're just visualizing or printing values. And actually, I have a print statement here that actually at this point of time. So I'll take that out. And then here it's looping over the layers and the next layer, and it's just generating the edges. Right? But we have a lot to cover, so let's just focus on this. So Spanish neurons, I've already set up the class. And what the class does, it's slightly different from the previous lecture. What it does is it takes in just the number of inputs. It doesn't take in the weights or the bias, which we did previously. And it takes in a tag. And then it creates the array with the weights, and it creates the value of the bias. And what we do this time is, because we're not passing the value in, we just use numpy.random.rand, which creates a random vector of a particular size. So for example, let me just start running these. And so if I say numpy.random.rand, right, just in case you haven't used this function before, if I say numpy.random.rand and I say 2, it will create an array with 2 random numbers between 0 and 1, which are ideal for weights. You do the same with the bias, and then this is what's going to be stored in the forward pass, the inputs, the Z and the A. And in the backward pass, we are going to store the sensitivities of the loss with respect to weights, the bias, and the inputs. So let's go write the forward pass. Let's say def forward. It's in self, and it takes in X, right, which is the input to the network. What's the first step? We're going to compute Z. We know how this works, right? So it's going to use numpy.dot. I'm going to say self.w and x. So this is basically wx, w1x1 plus w2x2 and so on, plus set.p. Right? And that's basically w1x1 plus w2x2 plus whatever, plus p. Right? So you can technically say it's vectorized, but it's only vectorized at the neuron level, right? And then we're going to say A is np.tanh and Z. And that's it. We're going to store our self.a is A, X is X because we need this for backdrop, and we're going to keep self.z even though we won't technically use it. And what I am going to do here is return the A. And that's our forward. So we're going to return the output of the neuron. Okay, clear? Let's now do the backward. So what is the backward taken? It takes the sensitivity of the loss with respect to the output of the neuron. This is everything is at the neuron level, right? And so what do? We say first we're going to change this step by step again just to make sure you see exactly how you're going through the neuron. So you're going to first get dA dz output with respect to z is basically the backward of the tanh. So it's 1.0 minus self dot a to the power of 2, right? That's the backward pass of the tanh function. And then we're going to say dl dz is dl dl dA dA dz, and then we're going to say dz d space dz dw is self dot x, right? Derivative with respect to w. We know what this is. It's w x1, x2, and so on. And then dz db is 1. We've seen this multiple times, right? It's just derivative of the linear layer, and dz with respect to the inputs. Self dot w in the single neuron models, this term was not really used, but now we've got a network, so we're going to pass this back, right? So what do we have? We have dl dw is dl dz times dz w. You know this by heart by now. You have dl db is dl dz times dz db, and you have dl dx is dl dz times dz dx. And what we're going to do now is store this locally. It's again slightly different from what we did previously, because that neuron was getting the backward and that was the output. In this case, we're actually caring about the network, right? So we're going to store these locally and we're going to say DL dw is equal to self.dl dw plus dl dw. What we're doing is now accumulating the gradients, right? Because when you do a backward pass across layers, you could have connections coming in from different layers. And so we have to accumulate the gradients, not just store the local, which was different from previously. Now you can do this easily by just saying plus equal to. So we're going to do that. And we're going to say self.dl dp is also plus equal to dl db. It's the local value just computed for this set of dl dA, but now accumulated. And then you have dl dx plus equal to dl dx. And that's that. We're not going to return anything from the backward this time, right? And at the layer level, we are going to extract what we need from the neuron, right? Okay. So we have got the backward pass as well. Now we need a couple more functions. We need one, what is called update weights. And the reason we need to do this is because we're not passing in a set of weights. We want to run this for a specific scenario. We need to give it the weights, right? And so this is quite simple. We're going to pass in W, and the structure of W is basically going to be W1, W2, and then B as well. And we're just going to say self.w is a numpy array in case what you passed in is a list. And it's going to take W from 0 to -1. So every value except the last. When you say 0 to -1, it doesn't include -1. So it doesn't take the last one. And self.b is np.array W -1. So that's that. And then we have one more function we need, which is clear gradient. Because we're doing accumulation right here, if you call backward on this neuron multiple times, and you don't intend to call it multiple times, it's not multiple neurons passing their value back to this. You've done it because you're running multiple optimization loops, or by mistake, then the gradients are going to keep getting accumulated and you're going to get the wrong value. So what we need to do is do clear gradients. And if you call clear gradients, all it needs to do is just set the gradients back to 0. And so that is all we need, right? Okay. So we're set with a neuron. Let's just run this once and let's clear this. We don't need this anymore. So what are we going to do? We're going to assemble the neurons first. We're going to assemble the neurons by hand, right? Meaning we're not going to use a class for layers. We're just going to see how we can set this up by hand. So let's just say the inputs, the first layer is always the input layer, right? So let's just see what the input layer is. This is the problem we've seen in the theory set. So it's a layer with value 0.1, 0.2, and 0.1. That's it. And so that's the inputs. And now what we do is let's initialize the neurons, right? So neurons, layer 1, that's hidden layer. So hidden layer 1. So what do we have? Let's do neurons, right? So N1 is neuron. And how many inputs does it have? The previous layer is the input layer. It's got two values, two inputs. So two inputs. The tag is N1. And we do have a set of weights. We're going to use that so that we can check what's happening. So use the update weights function. And we're going to make sure we wrap our list in numpy array so that we get an array that we pass in. And so we can use numpy operation, right? Numpy dot dot. And the weights and the bias for 0.1, 0.3, and 0.1. Let's just see if it initializes correctly. It does initialize. We're in a good place. What are we going to do next? I'm going to copy this. So actually I just need till here. I'm going to copy this. And how many neurons do we have? So first layer we have, or first hidden layer, we have two neurons, N1 and N2. So let's just set up N1 and N2 quickly. So we can do this fairly fast. And so that's N2. And this again, got it. Hidden layer 2. And what do we have now? We have N3 and N4. So you have N3, right? and N3 is 5.1.1. Okay. And N4 and 4 is 0 0.1, 0.2, and 0.3. And then you have the output layer. So it's, yeah, just call it the output. And what is there in the output layer? You have N5. So you have N5, you have N5 dot update weights. And what were the weights? It was 0 0.1, 0 0.2, and 0 0.5. And so we have just initialized 5 neurons and given them the weights from the example. What's next? Let's do the forward pass. So what I'm going to do is now I've set these inputs here so that you can see the input layer. It makes it easier to define the number of inputs. The advantage we had here also is each neuron has 2 inputs because the first layer is taking 2 inputs from the input layer. The second layer is taking the outputs from the first layer. It's got 2 neurons, so it's 2 outputs. So this has 2 inputs. And the final layer is taking the outputs from the second hidden layer, right? Which also has the 2 neurons, 2 outputs, right? So we could just keep the number of inputs to each neuron as 2, right? If it's a different structure, you need to keep that in. Okay, so we've got that. What do we do now? Let me just move this X, right? Here, right? Because actually this is where we want to run. So let's do forward pass 1, right? Which is hidden layer 1. What do? We say A11, which is the output from neuron 1, layer 1, right? Is N1 dot forward. What is it taken? It takes in the inputs, right? Both the inputs. Okay, and let's just print right here so we can see what's happening. Okay, and you say A11, A1. Let's just rerun this cell and run this again, and you get 0.1488, which we know is the correct answer. Right? You can see this from the example, and I'm also showing the network on the right, so you can see what we're doing. Now, what do we have? We have A1, 2, right? Layer 1, neuron 2, takes in the same inputs X, right? It's the same layer, second neuron, and it returns the outputs for that layer. It's not A21, it's A1, right? Layer 1, neuron. Let's run that. So you've got 0.25429, which we know is the right answer. Now, again, to speed things up, I'm just going to copy this, right? Because the second layer, we know, also has 2 neurons, right? And so actually, let's keep things clear. Shortcuts. H is hidden in layer 2. So what do we have here now? You have N3 and N4, but there is a small difference, right? So for layer 1, the output, let's write the output at the layer level, and we say A1 is now an array consisting of A11 and A12, right? And so that's the output of layer 1. Why is that important? Because layer 2 takes that output, right? And so you have, it takes in A1, and what you get now is layer 2, neuron 1, and layer 2, neuron 2, right? So we're just quickly modifying that, and we have what we need. Let's run that. And it's saying A1 is not defined because I need to rerun this cell, and we've got 0.1972 so on and 0.35026. And so we've got the correct answers for that as well. We've taken the outputs of layer 1 and passed it into the neurons in layer 2 and got the output. And what we're left with is the forward pass of output layer, right? So we have A. So first, we'll have to rerun this. What do we have? We're saying A2, right, is np.array, right, A1, A21, and A2, 2, right? So the outputs of layer 2, we're making that an array, and we're saying A31 is N5 dot forward, because N5 is the neuron in the third layer, and we're passing A2 to it. And in this case, this is the output of the neural network, right? So A31 is Y hat, effectively, is A3. Let's just run this again, rerun it. We've got Y hat, which is 0.5297. So we've done a forward pass by just connecting the neurons manually. Okay? Hopefully you've followed this. What do we do now? Let's do the backward pass. So first, let's just set up the loss. And so the loss value, we're just saying, doesn't matter because we're not really trying to train the network. We're just doing a forward and a backward. What we care is the DL dy hat, right? Which is DL DA3. So DL dy hat is 1.0, which is the value we used in exam. Let's just run that. And now what do? We start doing the backward pass through this assembled network, right? And then we'll obviously automate this to a significant extent. When you do backward, what you do, you start with the output. And so what are we doing? So the first thing we'll do when we do the back pass actually is first, let's just make sure that, and so this is something, let's just make sure that N5 dot clear gradients, we call the clear gradients on all the neurons, right? Just to make sure that we don't, mess this up. So anytime you call a fresh backward, you make sure you clear the gradients, right? For T2, run that. And it says n inputs is not defined because you need to say self.n inputs. That's my mistake. Let's rerun that. So we have to rerun the neurons initialization. Let's rerun the forward through that. And then let's rerun the back. That's how that works. Okay. So let's start with the output layer. So the output layer, what does it do? We just say n5 dot backward. And what do we pass in? It's the output layer. We pass in the sensitivity with respect to the output, right? And then we want to print what it's doing. Now in this case, it's just DLD Y hat going in. So that's all actually we need. Now we can print for that layer, we can print DL DW, okay? And that is going to be n5.dldw, n5.dldb, and then we can also print what needs to be passed back to the previous layer, right? Again, we want to visualize this for us. So it's being stored as dldx because we're saying for each neuron, the input is dldx, right? Even though actually it's the output of the previous layer, we're storing it in that value. So use n5.dldx. Let's run this. And what do we have? We've got 0.1418, 0.251, and 0.7193, which is correct. We know this from the example we worked out, right? And we have the values we need to pass back, dldx. So that's quite simple. Now, if you run this again, what happens? Let's just run this again. You see the values have gotten added and so have doubled up, right? Which is why you need to make sure that you clear the gradients and then you run this again. Okay. So now what do? We need to run the same thing on hidden layer 1, hidden layer 2. And so what do? We can just n4 dot backward. But now what are we using? We're going to use n5 dot lx, right? And is that it? Question. And the answer there is that's not it, right? So let's set this up separately. What does dl dx give you? Dl dx, as we know, gives you the derivative with respect to both the input from n4 and the input from n3. And so dl dx actually for n5 dl dx is basically an array, right, which has dl da3 and dl DLDA4. Okay. So what we need to do, we need to extract this. We're going to say DLDA4 is rather, actually what we can do is we can do DLDA3. Easier to do that from in order, is basically n5 dot DLDX0, and we can say DLDA4 is n5 dot x1. I'm doing this so that you can see this step by step, that ideally we're not going to connect these neural networks, these neurons manually anyway. So what you can pass back when you do, let's do n3 dot backward first. Okay. So n3 dot backward is DLDA3, right? And you can, after that, we can print, and let me just copy this. And so at the end of that, we can print n3.dldw, n3.dldb, and n3.dldx, right? And then what we can do is say n4 dot backward, right? And what you're passing back now is DA4, right? Because that's the output coming out from that neuron, and that's the input we want back. Okay. And so you paste this again, but now it's n4.dldw, n4.dldb, and n4.dldx. Let's run that. What do you get? So you get 0.0102 and so on, 0.017 and 0.0691, which is correct. And what's being passed back is 0.03, 0.06, which is also correct. And for the DLD4, what you get is 0.018, 0.032, 0.12, and what's being passed back as well. So we know they are correct. We've checked this by hand. So we've got hidden layer 2. That leads us to hidden layer 1. Now we're going to do something interesting here. And ideally you do this in layer 2 itself, but I've run that cell, and if I run backward again, as you know, the values get doubled. You've got, as you've seen here, DLDA3 is this, and DLDA4 is this. We have to do the same thing. So for this hidden layer 1, and we can do it, actually we can do it right there. We're going to say DLDA2, guys, is n3.dldx0, DLDA1, that is, right? The first one is n3 now gets the inputs from A1 and A2. So that's that, but it also sends its inputs to N4, so it gets the backward value from there. And we've seen this in theory, how this works, right? So the two ways to do this, you can either call N2 dot backwards twice, once with DLDX 0 from N3 and once with DLDX from N4, and it will accumulate it. So you know that will work. What I'm going to do is, because it's the same layer, we're going to make sure that the layer, when we assemble it as layers, outputs the correct value for that layer. So it accumulates across the layer, right? So that the layer is giving one set of values. So I won't call the backward twice. I'm just going to set this up right here, right? And so that's n4.dld, n3.dldx0 plus n4.dldx, and it's not 0, it's 1. And so now what we can do is do exactly the same thing, but now you're calling n2 dot backward, right? And you're passing in DLDA. So let's start with n1 dot backward, DLDA1, and we have n2 dot backward, DLDA. That's it. Simple. Let's just copy this print so that we can just print the values we've got, and we have back propagated to our neural network, right? So this is n2, and this is n1, right? Sorry, it's my bad. And this is n2. And we can run this, and you get the values for that network. And so you get 0.06, 0.03, yeah, and 0.03, 0.06, and for DLDW, for the first neuron, you consider 0.09, 0.04, 0.046, and so on. So these values are correct. Now, what I was saying is, what you could do is instead of adding this, you could just say n1 dot backward, n3 dot dl dx 0. So you could redo this by saying n1 dot backward, right? And pass it n3 dot dl dx 0, and then run n1 dot backward again and pass it n4 dot dl dx 0. And what the neuron would do is accumulate the gradients, right? And you could do exactly the same thing, right, for n2, right? But because they're from the same layer, I'd like the layer to output, the accumulated values for the neurons in that layer. That's the way I'd like to set it up. So that's why I'm doing this. And hopefully you understand this very well. We have backpropagated successfully through that layer, right? Or rather through the network, right? And so it's that simple. We've just assembled the neurons and then connected them manually and sensibly, and we've got a forward and a backward. So we can just visualize this using the visualization thing we've done. So I'm just going to say layers for network is equal to, and it's a list as I said, and the list has layer 1, which has neuron 1 and neuron 2, layer 2, which is neuron 3 and neuron 4. These are the actual neurons we have set up, right? And layer 3 is neuron 5. And then what are we going to do? We're going to say dot n is whiz. I'm going to call the whiz neurons function, which we just set up above, right? When we started the lecture, it was already there. And we're going to say n, and let's run this cell. And we see how it generates this really nice graph for us with the inputs and the outputs. And the sensitivities, we can just check the sensitivities quickly. We've got the weights here, we've got the sensitivities with respect to the weights, as you can see, right? And they're correct. We've got the outputs of the neurons coming out, and so on. So this is a really nice way to visualize how, visualize the neural network and see how that's working, right? So this is kind of given us a visual idea of what's happening. Okay, so that's the first part of this lecture. We have taken the neurons and connected them into a network manually. So what are we left with now? Actually, we're going to now create a layer class, and that is now going to help us assemble these neurons in a better way, right? So take a quick break if you want, and then let's do that. Okay, so let's now start assembling the neurons into layers, right? So assembling, or rather, let's say creating a layer. So what we are going to do is now create a class for layer, right? And what is that layer going to do? It's going to take in the number of inputs to that layer. We know a layer has inputs. You can take in the number of neurons in the layer, which is effectively the number of outputs in that layer, right? What you're also going to do is you're going to take in a tag, right? Which I'm going to say is, you can pass one in. But what you also need to do before that is you need to make sure, for now, you pass in the neuron that you want the layer to be built. And as we know, a layer can only have the same types of neurons. You can't have two different sets of neurons in the same. Now, right now, we only have that one neuron, and so that's the default. But if you want to go and modify this and add different types of neurons, as long as they have the same functions, forward, backward, clear gradients, update weights, you'll be fine. So now what do we do? Let's initialize a few basic parameters. So we want to create a list of neurons in that layer, right? And so it's basically neuron, which is in this case going to be our Tanh neuron we've created. And we're going to say neuron. What does the neuron take in? It takes in the number of inputs, right? Right. For I in range number of neurons. So this creates a list of neurons of the Tanh neuron that we've created above, right? Now what do? We say self.n neurons, so that in case we want the number of neurons, you just have that value right there. And then you can have another thing called the self.number of parameters. What is the number of parameters? Simple, right? Each neuron has two bias, two weights, and n number of weights you pass in. So depending on the number of inputs, plus a bias. And how many neurons do we have? So you have n neurons. So it's n neurons times n inputs, right? Plus one, right? Okay. Now the reason this works is we're assuming that they're the tanh neuron. If you have a neuron with just the tanh neuron you've created, meaning it has the linear layer, you have, say, a neuron without the linear layer, you're going to have to change this, right? But for now, I think this is good enough. And so you have self.n inputs. And this is not necessarily the most general implementation, but it will work, suffice for our purposes. What else do you need to have? You need self.a. And so self.a is numpy.zeros, number of inputs, right? And self.x, well, actually, number of neurons, number of outputs, right? My bad. And x is np.zeros, number of inputs. So x is the inputs and a is the outputs. What else are we going to store? We're going to store the accumulated gradients with respect to the weights. And so it's going to be np.zeros. Okay. So how many there are? The n neurons, right? And number of parameters. So it's basically going to be a row for each neuron, and each neuron has n input parameters. And I'm going to store the value of the bias here as well. Self.dldx, then p dot zeros. This is much simpler. It's the loss with respect to the number of inputs, right? So it's the number of inputs. Right? Because it's with respect to the loss, which is a scalar. And there are n inputs. So that's the init. Let's now write the forward, right? So forward, what does the layer take in? It's simple, it just takes in the number of inputs. We've seen that, right? Each neuron in the layer takes in the inputs. So it takes in not the number of inputs, it takes in the inputs. And what do? We loop over the neurons. It's a scalar implementation. Right? So it's basically an assembly of neurons. So we loop to over the number of neurons. So you can say self.n neurons. And then what do you do? For each neuron, you self.neuron I, you call them forward. And you pass in the x that's come into that layer. What do you get out of it? You get a I for now, which is the output of that neuron. But actually, what we can do is say self.a value I, right? A is an array of size n neurons. So in the corresponding index, you store the corresponding value of the forward pass. What you can do is return self.a, and that is it. So the forward pass is really simple. We're just looping over the neurons and passing the input to each of those neurons, right? Input to the layer, each of those neurons. We're storing the output in an ordered way and passing that output out. It's good. We're done. That's very simple. Now, the backward pass. So what do? We say def backward, right? What does the backward to a neuron takes? It takes in the derivative of the loss with respect to the values in the previous layer, right? Or the layer that is connected to it ahead of it, right? In this case, in this example, it's very simple. The layers are just directly connected one after the other. So it is effectively the next. So we get dA, which is the derivative with respect to the outputs. And we're going to assume that dA is basically arranged this way. It's called dA1, which is the derivative of the loss with respect to neuron 1 in this layer, right? Local, it is local. dA2, dA3, and so on. We're going to assume that, like we did with the assembly, the layer accumulates all the DLDAs for each neuron and then sends you the accumulated value. We're going to make that assumption. What are we going to do? We're going to go for I in range 0 to self dot and neurons. We're going to loop over each neuron in that layer. And what are we going to do? We're going to call self dot neurons. So it's neurons. Self dot neurons I. dot quit, right? And what is it going to take in? It's going to take in DL, DA, but not the entire DL, DA, right? Only of the corresponding neuron. We only want to pass back the sensitivity of the loss with respect to the output of that particular neuron. So we just pass that back. We know the way it's arranged, right? Once that's done, what do we do? What we need to do is we need to make sure we are accumulating the gradients. So we're going to say self.dl dx, right, is self.dl dx plus self.neurons I dot dl dx. And we're going to do this with dldw as well, right, is self.dl dw. Now dldw is I rows and columns. So the columns are the parameters. So dldw, right, plus, and we're going to say we're going to create this array because it's the weight and the bias. So it's going to be self.neurons I dot dl dw self.neurons I dot dl d. So that's the backward pass, right? Now, actually, because we are accumulating over the neurons, in the neuron itself, um, no, we could, because we are taking the value for each neuron and we're accumulating that, right? So we're good. We're just making sure that each time we're basically accumulating the DLDAs across the neuron so that when we pass it back, right, to the previous layer, we've got those values. And you don't need this here because the neurons will pass you, right, their individual values, and they will make sure that what is passed is already accumulated at the neuron. So we're good with that. And what are we going to do? We are going to say that's the backward. So we've got the forward and the backward. What else do we need? We need update weights. It's going to be self, and it's going to take in a weight vector. And we're going to assume that the weight vector has weights of neuron 1 and then weights of neuron 2 and so on for that layer. So what we do is we just go for a range 0 to len, or rather 0 to self dot n neurons, right? And then for each neuron, self dot neurons, I dot update weights, right? Self dot neuron dot update weights. And what are we going to do with the update weights? We are going to pass in, so it's a function. We're going to say W, which is passed in, Wi, right, times self dot and inputs plus 1, 2, right, 2, I plus 1 times, so again, this should be in brackets. Right, okay. What does this do? When I 0, we're going to go from 0 to, this will become 1 and self dot inputs plus 1. So it's going to pass 0, 1, and 2, which is basically, in this case, going to be the weights of our first neuron. Then I becomes 1. It's going to take number of inputs plus 1 is the number of parameters. So it's going to take, say, 3, 4, 5 and pass that to the second neuron and so on. So it's basically just taking the parameters associated with that neuron from this list or this array and passing it to the corresponding. So that's update weights. And we can have the gradients as well. And so we're going to define the clear gradients function. So it's going to be self. Now what it's going to do first, it's going to go from I in range, right, 0 self and neurons. And what is it going to do? It's going to call the clear gradients function for each neuron, right? That's very simple. So we're going to say clear gradients. What else is it going to do? It's going to clear its own gradients, right? So we're going to take these two, okay, and we're just going to, because we're storing the gradients at the layer level as well. So we're just going to clear that. This would be self.neurons. It would be self.inputs. Right? So in this particular setup, we are storing the gradients in two places. We're storing it at the layer level and in the neuron. Storing it in the neuron allows us to visualize it as well. So I'd like to keep it there. And it makes the computation, the assembly clean. And we're having a duplicate here. Um, when we set this up for production, of course, we'd vectorize it and we'd make sure we don't have this redundancy. But for this particular example, we were good enough. So I think we're basically set. This is n neurons, but we've basically defined a limit. So let's do this. And now let's set up a problem quickly. But now we can set up the same neural network much, much quicker using layers. So we're just going to say L1 is layer and it's got two inputs, two neurons. The neuron is of type neuron and the tag is L1, right? And we're going to say L1 dot update weights. And what are the weights? We're passing both the weights of neuron 1 and neuron 2, right? And the update weights at the layer level will take care of that. We're going to say 0.1, 0.3, 0.1, and 0.2, 0.2, and 0. We can also say L1 dot neuron 0 dot weights, so on, but I think it's good enough. So it's initialized those neurons. It's very nice. Let's now do the same thing for L2 and L3. So L2 is layer 2. It's also got two neurons and it's two inputs, right? The outputs of layer 1. And what are the weights? The weights are 0.5, 0.1, 0.1, and 0.1, 0.2, and 0.3. And what about layer 3? Layer 3 has two inputs, the outputs of layer 2, but it's got only one output, right? It's one neuron. And so it's L3. And we're going to say L3 that update weights. And so it only has two weights and a bias, so three parameters, and 0.1, 0.2, and 0.5. Let's run this. So we've initialized. Let's define the derivative of the loss with respect to the output of the network. And so that's np dot array, and we've done this previously. It's 1, 2. We need to do one more thing before this. We need to make sure the gradients are clear. So we're going to say, we haven't run the forward pass, right? So first, let's run the forward pass. So what's the forward pass? The forward pass is very simple now because we have set this up as a layer. We're just going to give it the inputs. So we're going to say np dot array, and the inputs were 0.2 and 0.1, right? 0.2, 0.1. What are we going to do? We're going to say L1 dot forward X. What does L1 return? Well, it accumulates the outputs of each neuron and gives you the output for the layer, right? So we're going to just say print A1 and it's A1. And then we're going to say A2 is L2 dot forward A1. We're going to print A2. And so that's layer 2 is taking in the output of layer 1 and giving you the output of layer 2, right? And then layer 3 is L3 dot forward and is taking in the output of layer 2. So now it's so much simpler to set this up, right? Once we have set this up in the form of layers. And if I run this, we got a forward pass and we know it's correct, right? 0.1488, 0.254, 0.197, 0.350, and 0.529. So we have got our forward passes sorted. And we've just set up the layers with the neurons, telling it the number of neurons, we've given it the weights, and we've run the forward. Now what do we need to do? Run the backwards. We've set up the derivative of the loss function with respect to the output of the neural networks with respect to A3 effectively. Now what do? We first clear the gradients to make sure that there's no accumulation. So let's first call this. So the gradients are clear. Now what you do? Say L3, what? dl dy, say run, right? Okay. Now L3 dot backward dval dy hat, but we haven't printed the value. So actually I should say print. And what do we want to print? We want the derivative of L3. So I'm just going to say DL3 here because I don't believe it's returning anything. The backward's not returning anything. And I've got to print DLDA, which is what is showing up. So the print DLDA, which I had added, is basically printing DLDA there, actually. So it's printing what's gone in. What we want to print is L3 dot DLDW, right? So we want DLDW3. And what we also want is DLDW, DLDX. So it's L3.DLDX. Now we've just run this one. So let's clear the gradients and rerun this. And so what do we end up with? We end up with that. If I don't run the neuron again, it's going to print the input to that layer. So that's what this is. I'm not rerunning it. So we've got the derivatives with respect to layer 3. Let's just check it. And so we've actually done this in just above, right? So it was 0.14, 0.25, and 0.07, and then we've got the two layers values being passed back. They're correct, right? To run backward again, it will accumulate. So don't run it second time unless you've cleared the gradients. So now we're going to run L2 backward. Now what goes into L2? The answer is very simple, right? At the layer level, what we've already done is also accumulated across the two inputs, right? We've accumulated, in this case, it's one neuron, so there is no accumulation required. But if there were two neurons, we have accumulated the outputs with respect to the outputs of the previous layer. So all you have to do is pass back L3 dot DL dx, right? And then what you can do is say print, and now you're printing DLDW and DLDX. L on this. So what do we get? So what's going in is 0.719 and 0.14. This is the value in. And what are we left with? We're left with, so we've printed DLDW and DLDX. Right? So what is DLDW for neuron 4 and 3, right? So for 3, it's, just give me a second, let me just check this. 0.102, 0.17, 0.06. And for layer 4, it's 0.018, 0.032, and 0.12. So we are correct. What's being passed back is 0.047, 0.032, which is obtained by summing what's being passed back from 3 and 4, right? So this value you see here, DLDX2, DLDX for layer 2 above is DLD, whatever is coming back, DLDX, right? For neuron 3 plus from rather, not for, plus DLDX from neuron 4. That's already being summed, so we don't have to do it specifically, which means we can say L1 dot backward, right? L2 dot DL dx, and what you should get is the correct value of DL dw for L1 because the accumulation passing back from both those neurons has already been done. So let's run that. And do we get the right value for layer 1? So we get for, this is what's gone in, and what you get is 0.0092, 0.004, 0.0046, and 0.006. So these are the correct values for layer 1. And we don't care about DLDX for layer 1 because there's nowhere to backpropagate it. So now, in much fewer operations, in much cleaner code, rather, it's the same number of operations, right? In fact, we have added a little more complexity with the layers, but in a much cleaner way, we have now created those layers and we have assembled them. Okay, so let's now write a simple wrapper for these layers so that we can we can call this from, or we can use this more easily when we do training in the future sessions, right? So let's just say this. So let's create a simple class called NN. What does it take in? You say it just takes in the layers, and you default that to, an empty list, and you say self dot layers is layers, self dot end layers is the length of this list, right? So that's just that. It's quite simple. And then what are we going to do? We're going to say, well, let's define the forward pass. So def forward. What does it do? It takes in the input to the neural network. And then it's really simple, right? You just go for IL in range 0 to self and end layers. We're just looping over the layers. Now here we're assuming that the layers are just sequentially connected. So layer 1 is connected to 2, 2 is connected to 3, and so on. We're assuming there are no complex connections. Like, so if you have, say, complex neural networks for image models and so on, you could have, or even transformers, you could have layer 1 is also connected to layer 5. We don't have that here. So we're just assuming 1 is connected to 2, 2 is connected to 3, and so on. For more complex network, if you're setting that up, you'd use a tool in production anyway, like PyTorch. And in that case, what you'd also have is the ability to connect across layers, but also to make sure to also have autograd. Right? We've not set that up. It's already quite detailed for this particular lecture. So for now, we're just going to assume sequential connections. So what you do, you just say, well, X, and then what you're going to do, you're going to say self dot layers L dot forward. Now, what are we passing into forward? So let's define a simple variable called AI, which is the input to the ith layer. It's also the output, right? But we're going to say AI, and we're going to say AI is X. So initially, AI is X. So when it's the first layer, right, IL is 0. So we're just going to take X and forward through that. And let's say the output we get from that, right, is AI plus 1. Only now, what is AI plus 1? We're going to say AI is AI plus 1. Because for the next layer, this output serves as the input. And that's your forward pass. What about your backward pass? You're going to say self backward, self. And what we need in the backward is the derivative of the loss with respect to the output of the layer, which is going to call itself is DL. You're going to say IL in range 0 to self dot end layers, which is the same. But now there's a small difference. We're going to say the output of this, and we've always used DLDX. We're going to call it DLDX, self dot layers. But now we're going to start from the last layer. So it's going to be -1 minus I. So when I is 0, IL is 0, it'll be the last layer. When IL is 1, it'll be the second last layer and so on. So we're going to move from the last layer backwards. We're going to call backward, right? And we're going to pass DL. So when it's 0, it's just the value passed in, which is the derivative with respect to the output of the network. And we're going to say DL is DL dx. So we get the backward. Actually, this is not passing DL dx. So we're going to say DL dx self dot layers -1 my -1 minus IL, right, dot DL dx, right. So in the backward, this value is computed. And then you're just going to store that here, and you're going to say DL now is DL dx. So to the previous layer, this derivative, which is passed back, is now passed here, right? So we've done the forward and the backward, and for now, that's it, right? So what do we do? Let's define that network. How do we do that? Well, we're just going to take these layers here, right? I'm just going to take this because it takes in a list of layers, right? So I'm going to paste this, right? And then I'm just going to say layer list is equal to the list of L1, L2, and L3. And I'm going to say net, which is the neural net. So let's do that in the separate thing. I'm going to say net is NN layer list. And let's run this. Let's run this. This works. Right. At least it's initializing. Let's say input. So x is np dot. We've written this a few times, but again, rewriting it right here, clarity. And we're going to say net dot forward x. Are we returning something from here? We're not. So let's make sure we return the final value, which is just the final AI, right? At the end, AI is set again. So the last layer will return an AI1, which is set to AI. We're returning that. And let's just make sure that we've got the output of the net. And let's print net out, which is the prediction. And that's a net. Let's run this. Well, we haven't set inputs. Let's run this. So I have to reinitialize, rerun that cell. Let's just rerun this. You've got 0.529763, right? Which is correct, right? We've set this up quite a few times and we know the answer to that. So we've got the correct answer for the forward. What do we do about backward? We just say the L is 1. Okay. And then we say, well, we have one more function, so we need to add here, which is def clear radius. And so we say for IL in range 0 to self.n layers. And we say self.layers IL dot clear. So now the values are only being stored at the layer level. Nothing is stored at the neuron level, right? At the network level. So as long as you clear the gradients for each layer, you're sorted. Let's go and just make sure we clear this. And we say DL is np dot array 1. Say a net dot backward L, and hopefully this runs. We can just clear the gradients, as I said, a net clear gradient. Let's run this. So it's saying numpy.ab. Oh, I haven't run a net. It's not a net, it's net, right? Sorry, my bad. A net is the value returned. It's net. And it says no clear gradient. It's called clear gradient. Sorry, that's my bad again. It should be clear gradient. Okay. So we're seeing that the values being passed in are correct to each layer because we had been printing that value being passed back to each layer in the backward. But what we're going to do is we're going to say for in range 0 to len net dot layers. Now we're going to say print, right? We can say layer I, and we're going to say net dot layers dot dl dw. Right? Sorry, it's my bad. And we've got 0.0092, 0.046, 0.046 for layer. So it should be I plus 1 because it's going to say layer 0, 1, 2. Well, it's okay. You know what we're referring to. And we know that these values are correct, right? We've seen this quite a few times. So we know that, and I'm just checking this now, but 0.10, 2.17, these are the correct values. So we've got now in just net dot forward and net dot clear grade, net dot backward, we have got forward and the backward pass through this neural net. So great, congratulations. If you've been coding with me or you've been watching, you've started right with a simple neuron, connected the neurons, and then assembled layers, and finally we've got to a point where we've set up a network and we've run a forward and backward. Now this will work for simple neural networks. If you have, like I said, complex connections, then we're going to have to do something more interesting. But this is our first neural network we've written in this series, so that's really good. And so hopefully you've really started understanding how neural networks work and how they're not very complicated, right? They're just simple neurons connected, right? It's assembled in layers, and then the layers are connected to pass data, pass the values forward, and then do back propagation to train the net, right? And we've used a simple layer with with the linear part and the Tanh activation. So hopefully you've understood a lot from this lecture. And now coming after this, we're going to have a couple of interesting topics. We're going to cover classification for multiple classes by using a network like this. And then we're also going to go and start vectorizing the layers, right? Which is very important if you're starting to look at production applications. And then finally, we'll kind of set up something, with a tool like PyTorch. So you see how it really works if you're using a production tool. Great. So hopefully you've enjoyed this session. See you in the next.